Been in an error.
Okay. All right. It looks like we're gonna start now, so we'll let Steve open us up.
Okay, great. I'm Steve Pomeroy, and we are Group 25, and we are doing the project UAV navigation in GPS denied environments.
My name is Jonathan Castellanos.
And my name is David Gallegos.
My name is Aaron Hancock.
And I am Ben Borden.
All right. Moving on to the next slide, we're going to present to you guys the goals of the project. The goal of the project is to develop an unmanned aerial vehicle capable of autonomous navigation in areas where GPS can fail. Our system uses a custom quad designed by the CAA Drone Club. The UAV combines visual, SLAM, and inertial measurements to achieve reliable telemetry in environments where GPS and signals are limited or unavailable. This use of telemetry is translated into accurate global position estimates, allowing the drone to navigate autonomously without GPS. Our drone uses a Raspberry Pi companion computer on board with the flight controller. The system collects a visual and inertial data from a monocular camera, which you can see in the image that's on the left. Um, he then uses Beams Fusion and Opsland to generate visual odometry in real time. The odometry is mapped into GPS cast, allowing the drone to navigate autonomously.
So in this next slide, we will go over hardware, software requirements, and majority of the key tests that we did in order to accomplish our project. As you can see on this image here on the left side, this is just a test bench of, of how we gathered data, how we made our algorithm work. Anyhow, we get into the hardware where we have an Aeroselfie H473 and 4-in-1 ESC to power the motors. This is not included in the picture here on the left, but will be on the next slide. The Raspberry Pi 5 as a companion computer, HGLRC M100 Pro for GPS. This is just for to get a ground truth for our algorithm. Miko MTF02P, which is our optical flow sensor, and our 12 megapixel Pi Cam 3, as you can see on the front side of the drone. Our software, we did use Vince Fusion and OrbSlam 3 algorithms for visual inertial odometry. We use Mavlink communication from Q ground control to get it onto the to get it to communicate with the Raspberry Pi 5. In the Raspberry Pi 5, the pipelining is processed in mostly Python, some C++, and some key tests that we did is we integrated and calibrated camera and IMU sensors. There's internal sensors on the flight controller, which is the IMU, which includes gyroscope, accelerometer, magnetometer. And we also configured the visual inertial odometry pipeline and SLAM algorithms. We went through a good bit part of the when we established the communication between the Raspberry Pi 5 and the flight controller. And actually, last but not least, we also converted local odometry into GPS positioning estimates with geodetic function, and then we went through test autonomous flights in GPS denied environments.
And for the drone hardware aspect of this project, which was independent from the Raspberry Pi part of the project, here we calibrated and tuned the drone using ArduPilot, and we had different hardware configurations that we used to get a consistent and successful flight out of the drone with many different revisions of flight controllers, propellers, motors, and different bases and arms. And we exchanged the different motors, the ECS, flight controllers. All of this was the whole point of that was to have a working combination that the drone would fly, which was many different revisions. And we also had an integrated GPS module that some of them worked better than other. I believe we had an M80 at first, and the M100 was a better module, and we used a mast to mount that as well. And for the, oh, go ahead, Jonathan.
sorry. Another thing that we also did in the process of the drone to get it to fly was tuning the motors. We had to map the motors and tell the program to where each motor was positioned at for it to be able to link it to stable flight. Otherwise, it will be basically not controllable. And then, yes.
Another huge problem that we had within our hardware was one of our GPS modules was not working properly. So a lot of times we weren't able to get a GPS lock, and this also including us being indoors. So um, all the magnetic field that we got sometimes was not able to get a GPS lock in the Q ground control.
One other thing I want to add as well is we made a switch. This does speak solely about the hardware, but in terms of switching out flight controllers, we did play around with the firmware. We made a swap between Betaflight and ArduPilot. The ultimate focus of the project was to configure ArduPilot for autonomous missions. However, we wanted to achieve um, we wanted to make sure that the system could fly, so we went with an easier alternative with Betaflight to get the drone off the ground initially. So that is one aspect that we explored. Okay, so now that we have an idea of how the hardware was constructed for the drone, we're going to take a look at some of the results we developed with the algorithms. So the first one we're going to take a look at is VINS Fusion. My name's Aaron Hancock. I was responsible for this aspect of the project. Here we use the drone payload system that we saw on slide 3 with the monocular camera and the IMU sensor. We were not flying the system at this point. We were only calibrating it and tuning it outdoors to be ready for the test flights when we move onwards to integration. So here, the way that we were tuning and calibrating the system, we used the one of the golf carts on the campus to drive around the bus loop. And David helped me immensely, and so did Steve with carrying everything on the golf cart. So we set up our rig and we made a couple loops around the administration building main bus loop as well as the small medical building loop. And we collected visual inertial odometry. We used the Raspberry Pi to collect that data and then process it live to develop the odometry trajectory you see in the images on the left. We then used our geodetic conversion algorithms to convert those odometry guesses into GPS guesses, and then we plotted and compared them against the actual drone GPS data we collected. You heard David mention that we had an issue with our GPS module. We were having consistent issues with our GPS, so you can actually see that in the image on the left. So it's interesting to note that our odometry is more precise here than our GPS. It's important to also note that the GPS or the odometry does drift slightly away from where the true position of the pathway for the bus loop is, but this is actually within a reasonable tolerance of what the standard GPS would offer. So,
If I can add,
sure.
and during this process, we also had trouble with our IMU rate raw data, so we weren't receiving the full 200 hertz at this point in some occasions. So we were getting like 50 hertz, which was another big issue of why our actual odometry guess is not, within accordance to the actual drone GPS.
So, and then moving, with that idea in mind, let's actually explain how the algorithm works. So the way VINS Fusion works is it develops keyframe, it develops descriptors within its environment using the monocular camera, and it tracks those key points in its environment as it moves. So as those topics move frame to frame within the monocular images, the IMU is polling continuously, and it's filling in the gaps between those camera keyframes and points. And in doing so, it's developing its change in distance and relative scale and meters by combining the IMU inertial measurement data with the monocular data to develop this trajectory. So with this algorithm, explained, we're going to move on to the next one that we use for an indoor environment. We're going to let Ben explain that here.
Yes. Our next our next algorithm we used was OrbSlam, which works similarly to Vin's fusion, but not quite the same. As you can see in the first video, which is taking an initial video, and it is creating a map out of the images, like how Vin's would, but it makes a 3D point cloud. And that can be seen on the left half of the video. And each point is what is those green squares on the right half of each video. As you can see in the second video on the bottom, we ran a second video file within the map created by the first, and it was able to reasonably determine where it was based on similar images, similar points, and it was able to pretty accurately determine location. The reason why we use OrbSlam inside and VINs outside is just that's how these algorithms were developed, and the way that each algorithm detects similarities depends heavily on lighting and the amount of features. So it's better indoors with OrbSlam because usually the points it detects are more visible indoors compared to outdoors, while VINs works better outdoors because there's just more obvious information to be received.
Right. We noticed that one of the big differences between OrbSlam and VINs is that VINs performs well in a feature-rich environment, and it can handle fast motions and turns very well, whereas OrbSlam was actually better for indoor environments that had reduced features. OrbSlam tends to focus more on corners with its algorithms. OrbSlam stands for orient fast and rotate brief. So we found during our initial tests indoors that OrbSlam was failing when it rotated too quickly, or when it found features, or was stuck with like completely blank walls per se. It would actually crash. So in moving to an outdoor setup, we decided to stick with VINs. So with the algorithms underway and explained, we moved into integration. We finally combined our drone payload that we were testing and tuning with our actual tuned autonomous drone system. So I'm going to play this video for us and fast forward for the sake of time. But this is setting up RG Pilot and Q ground control to conduct our autonomous mission here at in Fort Lauderdale. We're at a park here in Fort Lauderdale. So here I'm going to arm the system, and I'm going to arm the algorithm, and then I'm going to trigger it to go into an autonomous flight mode, which is a button set up on the receiver. So here we are, we're taking off, and then we'll switch it to autonomous mode. You can see my hands aren't on the controller there. And personally, I could never fly a drone this well. But there it goes. It's collecting its visual inertial odometry all autonomously. And it's going to come back to us and then land. I'll go ahead and disarm the drone and then disarm the algorithm. And we'll see the results that we collected from that on the following slide. Now, because the Raspberry Pi 5 isn't capable of running the visualizer for VIN's Fusion, it has too much of a CPU overhead. what I did was we downloaded the file to our laptop, and we ran it locally on the laptop for the sake of visualization of the odometry that was collected. So I'm gonna scrub through the video because it's quite long. But here you can see it's the exact same takeoff. The drone's taking off and flying through its trajectory. And we can watch this part. It's rather nice. So I'm going to scrub through just bit by bit here until we get nearer to the end where you'll see me waving in the frame. Okay. And there's it doing its own autonomous landing right after its autonomous flight. And that's it. One of the cool points about this video too is you can see the actual height. The rangefinder on the drone collects the height data as well, and we can see that in the trajectory it developed here. And the last slide we have to show for you is going to be the comparison between the GPS trajectory, between the odometry that was developed into a GPS guess and the actual drone GPS, and then the plot of the trajectory on the side. Again, we were at Mills Pond Park in Fort Lauderdale. We were able to request clearance to fly there over the Thanksgiving break through the Autopilot app. And, that's brings us really to the end of our project. The only thing that we really have next or left is to effectively pipe these GPS topics, not GPS topics, the odometry topics into our Python script in a more live fashion, and then take the resulting topics that we create from that Python script and subscribe them to our GPS system that's controlling these autonomous flights. And then that way the drone will be able to pilot itself fully autonomously using a trajectory that's developed into a GPS guess to effectively fool the autopilot system. So that's it. That's the results. We did it. So thank you so much. It was wonderful working with everyone, and gonna wish everyone the good luck on their finals and an amazing rest of the semester.
Thank you. Likewise.
Thank you.
Thank you.
Thank you, guys.
Thank you.
We decided to include a little bit extra of a demonstration here at the end of the presentation. This is first-person footage from the Raspberry Pi Camera 3 module that's collecting our visual data on the drone platform. Here we're flying the drone 25 meters high autonomously around Mills Pond Park in Fort Lauderdale, around a much larger perimeter than we were for the initial testing. So enjoy the footage. Thank you.